Yeah, thank you everyone for having a morning time installment of these webinar series. It's 5 p.m. my time, so I'm just finishing up my workday, but I'm super excited to be giving this talk. Today I'll be talking about quantum technologies in space. Sorry?
Sorry, I got it muted. We're good.
Okay, no worries. Okay, so today I'll be talking about quantum technologies in space, and particularly I'll be focusing on free space quantum key distribution and the ROKS mission, which I'm a part of. I work at jointly at Craft Prospect, which is a space engineering practice based in Glasgow in Scotland, as well as at the University of Strathclyde as a research associate working with Professor Daniel Owe. Currently, my work basically focuses on a lot of protocol work, research, and modeling of how do we actually get a constellation of CubeSats up in the Earth's orbit and make a dream of having a quantum internet possible. Now, I will go into, I know that we have a very mixed background at this audience, so I thought I will start with a very nice animation of what is quantum and why we are doing quantum. So as many of us know, quantum is a study of the extremely small, less than 10 to the power minus 15 meters, the size of an atom. And often, most of the time, we focus on manipulation of quantum particles, such as single photons and electrons, which was not possible even basically in the near past. But before I go into quantum in space, I want to talk a little bit about my journey and how I came into quantum in space. So since I've been a kid, I was always extremely interested in space, in anything that caught my attention, any kind of mystery. So I started dreaming about working on black holes when I was in school. And then I found myself researching black holes and quantum gravity during my master's as well as my PhD. I did 2 masters, one in India at the Indian Institute of Science, Education and Research, which are some of the top research hubs in the country, which gave me a lot of, which opened me up to the possibility of the amount of variety of research that was there in the world. Next, I went to Perimeter Institute in Canada and worked at the University of Waterloo. There I worked more on theoretical physics, but I also focused quite a lot in different kinds of quantum theory. So I have a background in quantum fundamentals of quantum theory and how do you actually take the fundamentals of quantum and start designing basic experiments. I had a chance to work in LIGO in the gravitational waves experiment in Caltech. And then after my PhD, I started looking at how do people actually apply quantum in real life, and that's when I stumbled upon a lot of quantum companies in Glasgow, in Scotland especially, which has somehow become the hub of space-based QKD and also other space-based communication systems, and developing CubeSats in all of Europe, actually. And so I found myself a crack prospect, and I also scored a postdoc at the University of Strathclyde, and here we are, me working in quantum in space, basically taking a leap from working on theoretical black holes into closer space, closer to Earth, and something that I can actually take and put there in orbit. Okay, so next, let's go into why are we actually interested to put quantum in space? Believe it or not, space is actually a wonderful laboratory which has microgravity. It does not have atmosphere. It has a high vacuum. It has long free fall times, and it has very low temperatures, as again, most of you will be aware of. And this actually helps us able to design much better experiments to have tests of equivalence principles, to test gravity and quantum gravity. It can also allow us to test long distance tests of entanglement of particles. It's a great place to be testing precision of clocks and sensing. It's a great place also to be looking for deviations from general relativity, which is currently the state of the art for how we understand gravity. And then not only that, we can take these fundamental physics experiments and we can use them and use space as an enabler or as an architecture to help us augment terrestrial communication networks. This is where QKD, quantum communication, quantum internet, quantum technologies all come in. I will talk a little bit about, so basically, yeah, these are the top few topics which are all the rage in the quantum community right now. People are looking at QKD, as I mentioned. People are also looking at quantum sensing. How can we put tiny little cold atom quantum sensors on top of CubeSats? I will be coming to what are CubeSats in the rest of my talk as well. People are starting to look at quantum metrology and a lot of various other quantum physics experiments. But today, I'll be talking about QKD. And the need to do that is that all of us know that quantum computers are almost out there. Admitted, there is a lot of hype around it, but hype or no hype, security services around the world can be hacked as soon as the quantum computers are on the market. So if we are trying to plan for the next 10 to 15 years, we should remember that we need future-proof cryptography protocols. Now, what does that actually mean, right? We need, right, so before I go into future-proof cryptography protocols, let me talk a little bit about public key cryptography. Today's world has a lot of data. All of us use internet, all of us use mobile phones, all of us go on the computer and put our data on the cloud. With so much data being thrown around everywhere, with it comes a lot of responsibility. The responsibility to make sure that this data is well protected. Currently, we do that using public key cryptography techniques, which are based on tough math algorithms. Basically, you take anything which is a huge calculation, a calculation that is even hard for computers having a lot of memory power or really high processing powers to also crack, but they are not uncrackable, right? So with better and better computers and even quantum computers on the horizon, it's just gonna become really easy to crack all of the public key cryptography that we have currently. There are a few different ways we can go ahead from here, and one of them is that we actually take the basic principles of quantum computers, which is quantum mechanics. We turn it on its head and we ask, okay, this is going to be providing a threat to our data, but how do we actually use quantum to protect our data? This is where quantum cryptography comes in. So basically, quantum cryptography uses quantum objects such as single photons to encrypt information, so that if someone else tries to capture these photons mid-channel and hack it, the quantum properties of these photons, such as no cloning theorems, will demand that they reveal themselves. So basically, we will always be able to find out if our security has been compromised, even by quantum computers, if we use quantum key distribution or other kinds of quantum cryptographic protocols. And that is why I was saying before that we have to ensure that it is future-proof, that it is protected against quantum computers in the future, it is protected against any other kind of hacks that we can think of in the future as well. A little animation again. So what is quantum key distribution, right? So in quantum key distribution, a lot of you must have been, again, hearing these words quite a lot. There is an Alice and there is a Bob. Alice is the one who is taking single photons. She's creating single photons, producing them, and she is encoding information in these single photons, which she will now send to Bob. Bob will take the single photons, he will decrypt them, and will find this information, which basically is called a key. Bob can then use that key to encrypt other information, and then Alice and Bob can have a secret communication between themselves. There are various ways of sending this information. Some people use fiber. So fiber-based QKD has already become commercial, with many different companies focusing on it. But with fiber optics, there are a lot of losses. The maximum propagation with fiber is 500 to 600 kilometers. So these are not very practical to be used for long distance communication. So, for example, if we actually want someone, two different countries which are more than 2,500 kilometers, or, well, if you're talking about India, in one country there's 200, 500 kilometers, right? If there's two countries around the world which are separated by a long distance, how do you actually use QKD to have a secret phone call, for example? That's the big question. Now, what we do is, let's take a little area in each of these countries. Let's set up two ground stations, right? Now, what we can do is both of these countries can agree, and then both of them will send a satellite up. This satellite is going to be trusted by both parties. I'm sorry, I think someone has their microphone unmuted, so if they can mute it, that would be helpful. Thank you so much. Just a second. What did I do with my screen? Yeah, there you go. there. We have already erected 2 ground stations on those 2 countries that want to have a secret communication between themselves. So these 2 countries come to an agreement and they have already sent up a satellite now, right? Now, what can happen is this satellite can first have a link with one of the ground stations. So when the satellite is flying over ground station A, it creates a link with ground station A. It sends down photons. So the satellite is now Alice. It sends down its photons to Bob 1, which is the left ground station. Bob 1 then distills a key out of this communication that the satellite and the ground station had. Now the satellite again flies over ground station 2, which is Bob 2. Alice, which is a satellite, and Bob 2 have a secret communication. They exchange information on photons, and they also have a key. Now, the satellite can act as a trusted relay between these 2 ground stations to basically create a common shared key between ground station A and B. Now, how can we actually do that? Basically, if we actually send the satellite onto a LEO orbit, which is around 500 to 600 kilometers above the ground level, and we remember that the distance of QKD is around 500, 600 kilometers maximum with fibers. So we're not really increasing the distance between the satellite and the ground stations. What we are doing is we are effectively reducing the distance between 2 long distance separated countries. So in this case, the photons are mostly traveling through free space. And so they're going to be avoiding most of the time the Earth's atmosphere, which comes with its own problems. It creates a lot of turbulence. It can create beam refraction, beam wandering. And so if we are avoiding the Earth's atmosphere for most of the 500, 600 kilometers, and the atmosphere is actually only 10 kilometers at certain places, this does not create as much of losses as in fiber-based QKD when we are trying to do long-distance communication. But it's not, obviously this is a very simplified picture. It's not as easy to do satellite QKD, whether it be their atmosphere or not. We have to figure out what kind of photon sources we are going to be putting on the satellite. We have to figure out kind of quantum random number generators we are putting on the satellite. We have to figure out what kind of sensors we are putting on it. We also have to figure out what kind of stuff the ground station needs to have to ensure that it can decode all the information from the satellite. How will it measure quantum states? How will it handle random numbers? How is it going to sync with the clock, which is on the satellite as well? So on the next few slides, we're going to go into a little bit about what kind of QKD we are doing on the ROKS mission. So here's a little, I love animation. So here we have a little animation of the Craft Prospect logo as a ribbon on Alice, because we are the satellite in this case. And we are working with the University of Bristol, who are designing a ground station. And since I'm in Scotland, I have put our Scottish kilt on the ground station. And we have our lovely Nessie as our Eve, who is our eavesdropper, who will be trying to steal information from our quantum channel, right? So Alice, which is going to be the ROKS mission, is going to be sending out photons. Now, single photon sources can be quite hard to get in the market. Single photon sources are also quite difficult to ensure that we can produce single photons at the frequency we require. So we are using something known as a weak coherent pulse, laser pulse, to send out almost single photons over the quantum channel. We also need a classical channel to do a lot of post-processing, right? So there are various different kinds of protocols here that can be applied. The BB84 protocol, which has been there for a long time, has been provably safe against attacks by eavesdroppers. And I'm again hearing some kind of noise in the background. So
Yeah, I think the person is trying to leave. Trying to actually,
right.
I can't mute them because it says they're leaving.
Yeah, that's fine. Do you want me to wait a bit? And oh, there you go.
Okay, there we go.
Right, and yeah, please feel free to ask any questions in between the talk or after as well. I'm happy to take any kind of discussion questions. Yeah, so there are various different kinds of protocols here that can be applied. If you go up and look at what is the BB84 protocol, it's one of the earliest protocols that has been proven to be safe against attacks by eavesdroppers. And so we're going to be trying and doing that. One thing to keep in mind is that the upcoming ROKS mission will be one of the first of its kind of mission, because we are trying to put a highly miniaturized quantum source, weak coherent laser pulse quantum source, on a CubeSat, which is the size of a cereal box carton, basically. And we are sending that up, and we will be trying to demonstrate that we can actually create a satellite to Earth link with our ground stations at Bristol and at various other places in the UK, and hopefully international ground stations as well. So this is the first step. You demonstrate that you can do something. You demonstrate that we can actually create a quantum link, that we can actually distill a secret key out. And after we do this demonstration mission successfully, we will be trying to roll it out as a commercial service. We will also be trying to do take it further and try to create a constellation of CubeSats. I'll come to why we need a constellation soon as well. But a little bit, I have like a little, again, infographic on the BB84 protocol. Now, I'm not going to go into the details of this because I don't think the time will permit that, but I want to tell you that basic building blocks of the protocol. So what we do on the satellite is we're going to be putting quantum random number generators on the satellite so that they can create true random numbers. Now, our quantum random number generators, what it does is it spits out 0, 1, 0, 1, 0, 1, 0, 1, and this is the mapping that we are going to be using. The mapping is here. So if it spits out a bit 0 in the first place, we will assume that if, so here we spit out 0 or 1 first, and then it again spits out 0 and 1 or 0 and 1. So if it's 0, 0, then we assume that it is the horizontal polarization basis, and it is the vertical polarization, which corresponds to 0. If it's 1, then it corresponds to the horizontal polarization, right? And if the basis was the antidiagonal or the diagonal basis, then the 0 corresponds to the diagonal and the 1 corresponds to the antidiagonal polarization. And this is how you encode information into photons. You encode the information into their polarization states. So when Alice is sending a bunch of photons, what she's actually sending is a bunch of different polarization states. So if Bob actually takes one of the polarization states and measures them in the correct basis, he will be able to tell whether it's 0 or 1 that Alice has sent. And so you can see that at the end, there will be multiple errors, but there will be some length of like a string of 1s and 0s that Bob will be able to distill out. After that, Alice and Bob will need to do some other kind of post-processing over a classical channel. They don't need to send any more photons down, and they can do it over a RF channel, some other communication where they try to figure out whether Eve has actually gotten any important information or not. And after that, they establish a raw key, right? Now, the story is not over yet. They also have to make, they have to do quite a lot of post-processing to ensure that this raw key that both of them have actually agrees. So if Alice has a key and Bob has a key, both of them have to be the same key. Otherwise, they would not be able to use that key to do secret communication. So they take a random part of little 10% of that key and they communicate over a classical channel. So basically, they broadcast out into the internet so that everyone can hear it. But it's only 10% of the long key that both of them have. So if those 10% comparisons agree, they say, OK, the key is secure, use key. If the comparisons do not agree, they say key unsecured, do not use key, try again. So basically, the satellite in its next pass has to go over Bob and try to send down another string of photons and hope that this time they can have the same key, which they can use, right? Now, in principle, it's very easy, but in reality, you have various different steps. There's the qubit transmission. After that, the one I showed you, we have a raw key, which is distilled. After that, you have the sifted key, where you're doing this comparison of 10% of the key that has been sent. Then you have various other states, like you have to estimate the quantum bit error rate. You have to estimate what kind of error correction you have to do. And then you'll have to do some kind of privacy amplification so that actually you reduce the probability that Eve has certain amount of information even further. Now, in order to do satellite QKD, to be various different considerations as opposed to fiber-based QKD. On fiber-based QKD, you can literally, well, it's not as simple as I'm going to make it sound, but what you can do is you can put one of your transmitter on the tabletop, you can connect your transmitter to a fiber optics fiber cable with some collimator, and then that can literally take the photons to a receiver on the tabletop as well. Now here, because we have a satellite flying over the Earth, we have to figure out what is its elevation at a particular point. We have to figure out whether we actually get some amount of viable key rate with respect to elevation. So in our case, we estimate that when the satellite is over 40 degrees from the horizon, only then we will be able to start doing QKD. Otherwise, our key rate is too low. We also have a lot of background light in the atmosphere. So if you're sending single photons down, your optics must be really, really sensitive. But also, you have to have a mechanism of making sure that you are distilling out stray light, which can come from the moon, which can be reflections from the Earth as well. So ROKS is currently scheduled to fly at night to minimize this. There will be a lot of refraction in the atmosphere. There will be loss due to the free space propagation. There will be loss due to the satellite basically tumbling around in the orbit. And how good you have a pointing and tracking system of the satellite, which is something known as an ADCS. Also, that depends on how much money you have and how big the satellite is. Next, if you're actually doing a small satellite versus a big satellite, so if you have a big satellite, you have a lot of money, and you have money for custom optics. So you can design optics exactly how you want it to. You can make sure that the noise is minimized. You can make sure that you have as big of an aperture as you require. But if you're trying to minimize costs, like startups like us are doing, we have to actually rely on a lot of commercial off-the-shelf components, so industrial components which we can just buy off from an online store somewhere. And so one of the biggest problems we are facing is we want to build a telescope which is small enough for our CubeSat, but that is proving to be quite a big challenge because we need to make sure that all the optics are athermalized. And also we want quite a big aperture size. So how do you fit a big aperture size into a small satellite, right? That's another thing. Other considerations are whether our satellite is going to be, like, how many times a satellite is going to go over the ground station, what time is it going to fly over the ground station, whether you want to collect all the keys in one particular pass of the satellite, or whether you want to wait for multiple passes of the satellite to collect all the keys down and then do the post-processing. All of this also depends quite a lot on what kind of platforms you're using, whether you're using Linux-based platforms or, and also what kind of memory you have on board, right? What kind of quantum random number generators are there in the market right now? Because a lot of the quantum random number generators in the market do not have the speed, like the frequency with which they are producing quantum random numbers to be used directly with the source frequency that we have. And so what we might need to be doing, what we might need to do is take a QRNG, somehow put the output of the QRNG in a buffer in our memory and then use that buffer. But somehow we also have to take all of this and do a security analysis, an end-to-end security analysis to ensure that, okay, QKD is only one part of ensuring secure communications, but there's a lot of classical mechanics around it. There's a lot of optics around it. There's a lot of maths around it, which also needs to be all proved for security, right? So for example, when we are setting this output of the QRNG in a buffer, can somebody have access to that? What are the risks associated if somebody has access to that? Are there ventilation holes in our system, and can random satellites orbiting around our satellite inject photons into it and do some other kind of cheating on the side, basically? All of this also has to go through quite a lot of stress and vibration testing, climate testing, vacuum testing, and so on to ensure that the CubeSat, well, the satellite does not break in its way onto the atmosphere. Also that it does not stop working over its life cycle, which is around a year to 2 years for us. But why do we want to use CubeSats? So for us, we are using CubeSats, which are really small satellites. But why do we want to use CubeSats as opposed to conventional satellites? It's because we are looking at a dream in the future where we are connecting various different parts of the Earth in a global network, which augments whatever terrestrial networks we have right now. And in order to do that, in order to send up quite a lot of satellites which are covering all of the globe, it'll be really hard to send up conventional satellites, because first of all, they would require a big team. They would require a lot of money. They would require quite a lot of customized optics, they would also they also have a higher risk, because if one of them fails, then you are actually losing quite a lot of money, and then you wouldn't be able to deploy another satellite in its place as fast as you would be able to do when you have small satellites, right? So smaller satellites, they have more risk appetites, they have less cost, they are easier and faster to deploy, and so we come to CubeSats. Now, I know that this should probably have come in the first slide of the talk or something, but this is what I mean when I say a CubeSat. So 1U of the CubeSat is basically a unit, a cube, which has 10 centimeters times 10 centimeters times 10 centimeters volume. And I have put a loaf of bread on the side to show you the scaling. Now, ROKS is basically a 6U CubeSat. So we have 6 of these cubes stacked, three on the left, 3 on the side, 3 on the right. And our QKD payload, this particular mission, ROKS, is going to be carrying quite a lot of payload. So it's going to be carrying our QKD payload, which is around 1U. So it's quite small. And we have had like a fun time taking everything that was lab scale and then working on it quite a lot to miniaturize all of the optics to ensure that we make a tiny little box which will fit inside 10 times 10 times 10 centimeter cubes, right? We also have some space for for our product known as a fly, which is a forward-looking imager. What the fly is going to be doing is that it's going to be having an imaging camera, which is going to be looking ahead of the orbit. So it's trying to find out whether the cloud cover over a particular ground station is too much. And it also carries a neural network on board so that it can make onboard decisions. It's the analogous system to a self-steering car. So it will be a self-steering satellite. Obviously, we are not completely there yet in the futuristic sense, but we will be able to make decisions if there are clouds over a particular ground station. This neural network can be like, okay, here's the cloud. This ground station is, out of your reach right now. So let's point the satellite a little bit to this side because there's another ground station, and we will be able to not lose this pass and use it to actually create establish some secret keys with one of the ground stations at least, right? Yeah, and these are exactly how the satellite boxes look like, the CubeSats. These are 3U CAD models of the skeleton. Now, what does actually go into the making of a CubeSat QKD payload? So on the right, you can see that this is a picture of the exoskeleton of the CubeSat, and it has got various layers in it. So some of the layers are, the CubeSat will have various different computer boards. There will be a software and protocol layer. There will be embedded systems, which is a lot of electronics, which have been miniaturized. There will be electrical and other hardwares. There will be a lot of optical systems like lasers, LEDs, mirrors, telescopes, and so on, which I have been kind of here and there talking about in my talk. The challenges with this is that theoretically work has matured quite a lot, but technologically we're doing quite a lot of this for the first time. A lot of innovation is required. So in our case, we have to take a lab scale quantum source and go through various different iterations to make it this little. I don't know if people can see this, but basically it's as small as I don't know, like half my thumb, basically. We are going to be testing a lot of these things for radiation hardiness. So we have a lot of electronics on board, and if there is one little particle in each of these electronics, that one little space particle, cosmic particle, which comes in, and it can basically destroy a lot of the electronics. A lot of tiny instruments might break during launch because we have lots of optics. So we have to figure out how do we screw everything in to lock them so that a CubeSat, which is vibrating quite a lot during launch of the rocket, does not break them. And then we have to figure out how do we actually fit everything in a tiny CubeSat, which have their own specifications. The manufacturer of the CubeSat have their own specifications, and UK Space Agency also have their own specifications. And then we all have to take a lot of lasers and play around with it, which is always a lot of fun. But the most important parts are we have a lot of commercial off-the-shelf components which we have bought, and how do we actually standardize them? How do we make sure that there are no security loopholes which we are missing because we have just picked up something, and it'll be harder to take it apart and figure out what exactly is going on in the system, right? Because we're not doing any custom work. And To make matters even more complicated, right now we don't really have that many regulations on the CubeSat orbital space. We don't have regulations on and standardizations on what kind of security should we have to make sure that this QKD system can very easily interface with internet, with any kind of mobile networks, basically whatever systems we already have in our world right now. Otherwise, it's meaningless, right? Right, and this is a picture of the payload box as it looks now on top of my table at my office. You can see the little blue frame. This is the actual CubeSat frame, the CubeSat bus that we will be using. This little box is basically the box, the QKD box, which has somehow fitted in quite a lot of miniaturized optics in there. I have taken out this the electrical board piece, which is going on the top of the box, and it has all of our embedded electronics in there. We have quite a lot of steering mirrors to ensure that we can somehow align and point the light where we want them to inside of here. And we will be putting the telescope somewhere outside of this box. Yeah, like if people can see this tiny little hole over there where my pointer is, that's outside of that hole will be the telescope, and this particular little mirror just behind the hole is we'll be able to steer it using voltages so that we can align the light to go out of the hole and directly into the telescope as we want it to, so that the telescope can then send that light out into free space. And we can also make sure that we steer the mirror as well as a satellite together to ensure that the light reaches the ground station. The ground station will also have a beacon of its own, which will reach up into the sky and try to find the beam that is going down from the satellite. They will both align. As soon as both of them have been aligned properly, we will start QKD, that is sending single photons, and hope that the ground station can capture those single photons, do proper measurements on them, figure out what key the satellite is trying to send, and establish a secure key. Now, there have been some missions already. The Chinese mission MyCS was the first one who demonstrated QKD on a conventional satellite for the first time ever, and it also used QKD to demonstrate a video conference possible between Austria and China using the secret key. There are various different missions coming up. One I have just listed a few of them. ROKS Space is a UK-Singapore-based consortium which is trying to demonstrate entangled photon source on board a CubeSat. ROKS, which is the mission I am involved in from Craft, will have a weak coherent pulse laser source on board and will try to demonstrate cloud-sensitive neural network supported QKD. KeySat, which is a nanosatellite launched by Canada, is going to also be showing an entangled source, which will be placed on the ground rather than the satellite, and a receiver on the satellite. And it will be doing QKD the other way around, sending photons from Earth onto a satellite. So basically, we want to go towards a quantum network. And so that is the reason why I'm working on making sure that we have this cheap, small, fast deployable, more risk appetite, having platforms such as CubeSats. Oh, I have these secondly, but yes, mostly that was what I wanted to say. So thank you everyone so much for listening to my talk. If you have any kind of questions, please feel free to bring them up and I'll be happy to engage. Thank you so much.
I wish there was like an easy insert clap track sort of thing. But thank you so much for a great talk. I'll ask maybe a couple questions while
Sure.
some folks are. If anybody has questions, you can feel free to put them in chat, or you can unmute yourself and ask. So I was going to ask about wavelengths. So I know that there's, just from my own background, there are a lot of different, I mean, the sky is blue for a reason in terms of that's what kind of colors can actually penetrate the atmosphere. So what sort of wavelengths is ROKS looking at to use to communicate to LEO?
So ROKS is currently looking at 785 nanometers. So you probably know this as well from your background. There's like basically most of these missions are looking at two kinds of wavelength ranges. So one is around the 1550, 1250 to 1550 nanometer, and then the other one is around from 750 to 900. I guess we started with looking at 900, but now we have basically gone down to 785 based on what kind of laser diodes are available, what kind of laser diodes we are able to miniaturize, and a lot of other little factors. But yeah, we're using 785 nanometers as the source wavelength currently.
Awesome. I see Praksha has their hand up.
Yeah, hi Sonali, Prakash here. So I just want to ask one question, like apart from the cryptography and the network sides, so do you see any other applications of the quantum in the space?
Yeah, thank you so much, Prakash. That's a really good question. There are a lot of applications of quantum in space. So one of them, if I can, so there are a few that I mentioned before. One thing that I'm really interested in, apart from QKD, is quantum sensors. So there are cold atom sensors where you take basically 2 photons and you can excite them, and they will be sending out a little, like some kind of electron or something. So how do I say it? Yeah, so if you look up cold atom sensors, I don't want to go into the details here. So you take atoms and you freeze them at very, very, very low temperatures, and you can now manipulate them to create very, very sensitive atomic clocks. Initially, atomic clocks used to be based on electrons, and now we can base them on photons, single photons, and we can manipulate them. And this will help us do quite a lot of fundamental physics experiments in space. This will also help us create receivers which can not only be in space, but also be on our cars, on boats, on any kind of terrestrial systems on the ground. So sometimes when GPS is not available, we will be able to use these kind of quantum atomic clocks, which would come a lot in handy. There are a lot of other kinds of quantum technologies which people are exploring right now. One of them is radar. There's quantum gravimeters, which again use cold atom sensors. You will be able to sense very small changes in the gravitational field of the Earth. We will be able to find out about what kind of gravitational, so we'll be able to find out where oil is, where water is, what kind of natural resources are under the Earth's surface. We will also be able to use these cold atom sensors to find out very small changes in magnetic fields around the Earth. And in that case, we will be able to predict what kind of solar storms are approaching the Earth. And so we'll be able to prevent any kind of damage to our power lines and electrical systems. These are only a few examples, but I'm sure that over time, we'll have many, many more quantum applications in space as well. Does that answer your question?
Yes, thank you. Thank you for detailed answer. Thank you very much.
No problem.
We have a question in chat, which is, what protocol do you think is most secure for QKD?
Well, I think, personally, this is a tricky one. I'm sure Sarah can tell you more about it, I think. Well, currently we are using BB84, but I think the most realistic way of doing this would be a combination of using some kind of post-quantum cryptography along with QKD, and taking into account how much time we actually spend on the pass, because that is basically the time that the quantum computer is going to have to hack a system. So if we can use any protocol which takes into consideration all of these systems, then we are secure. I think what is the most secure depends on your system, depends where your ground station is, depends what kind of optics you're able to use, how much, what kind of access you're able to deny to eavesdroppers. So that's kind of a complicated question, and I don't think I can just pick out one protocol from many now. I hope that was reasonable.
No, I think that makes sense. Like, and really, like, there's, as you say, there are trade-offs to each different protocols. Some of them can deny certain types of attacks while not necessarily protecting against others. And it really comes down to what are your assumptions? Like, what do you think your attacker can do? There are technically formulations for QKD called device independent QKD, where you
that would be
literally,
the ideal case. Yeah.
that's the ideal case. Literally, the only assumption you make about your system is that your attacker can't break the speed of light or can't go faster than the speed of light, which seems like a pretty conservative assumption. But the problem is it's way too impractical. You basically have to, you can generate one bit with a set of equipment, and then you have to throw all of the equipment away and then generate another bit. So, but yeah, suffice it to say, I'm not sure. I'd agree with your kind of assessment that I don't think there's necessarily a most secure protocol, and really just comes down to.
Let's say that ideally, we would love to have device independent QKD, and that would be the most secure ever, but we are nowhere there yet.
Yes, and I agree that Pyman, I did a lot of stuff on device independent QKD as well, just because I thought it was really cool. Obviously, understanding that we won't be able to do it, but gotta have goals, right?
Yeah.
Cool. Does anybody else have any other questions? Some folks in the chat said, thank you for an awesome presentation. It was very clear and concise. Thank you very much.
Oh, that's good to know.
Yeah. I
was very confused with all the silence, so I was assuming that either it's going really bad or really good.
It is hard to talk to effectively in an empty room, as we're kind of getting used to in these situations. But it was a great talk. I think you really covered a lot of especially with these considerations. That's pretty much going down the laundry list of what you actually need to think about when you're building these systems.
Yeah.
So.
I'm gonna use that word next, fun. Laundry list. That's for my next presentation.
I mean, laundry implies chores. I mean, some of these are not chores. Some of them are, but yeah, like
we're building up our lab now, so we don't exactly have a clean room because we're a startup. Thank you very much. But we do have at least like a small space set off now in our new office, and we are building our lab. So we have to take a lot of these things into consideration, like what kind of equipment we are buying. Again, be future considerate when you don't want to only be building for one mission. You want to be using quite a lot of your test equipment for future missions as well. So it's quite detailed, but I think it's quite fun as well.
Oh yeah. Yeah, Giorgio says it's been an excellent presentation, even for someone just tapping on the subject. Thank you.
Awesome. Thank you so much. I'm glad you liked it.